Greetings to everyone. I am Aman Surana from Group 2, and today we will be discussing about economic equivalence and financial modeling and chemical engineering. Today we are making a lot of interest, and for that we need to make sure that the economics are at the right place. While our designs are governed by thermodynamic and kinetic principles, our ability to actually build them is governed by economics, and we'll explore how present, future, and real world equations allow us to make rigorous data-driven decisions along with different financial modeling tools and economic terms. So these are the contents of the PPT, and moving on to economic equivalence and time value of money. At its core, economics equivalence means that two different cash flows have the same value at the same point in time, provided we apply a specific interest rate. This is rooted in time value of money. A rupee today is worth more than a rupee in the future because capital has the power to earn interest or the burden of costing it. For us, the interest rate reflects risk, inflation, and opportunity cost. We use the fundamental formulas listed in the PPTs and in the financial modeling equations to understand compounding and for discounting to move money across a project's timeline. Coming to the cash flow diagrams in chemical engineering, before we calculate anything, we must visualize the project to the cash flow diagram. In chemical engineering, we follow a strict convention. Downward arrow represents outflows, and it can be like initial purchase of a distillation column, or as well as a recurring cost like a raw material. And upward arrow represents our inflows, which include product revenue, energy savings from heat integration, hinge technology, or the salvage value of the equipment at its life. And the CFD is also the initial and essential step for any process evaluation. And coming to MARR and cost of capital in process industries. What's MARR? It's minimum attractive rate of return. And how do we choose our interest rate? We use this MAR technique. This is like our hurdle rate. For chemical companies, R is usually like 12 to 20%, and it depends on project to project basis. MAR is the minimum rate of return a company requires before approving a capital expenditure, and it should be higher than the IRR, that is internal rate of return, so that the project is economically attractive. And let's say, for example, we are making a high risk pharmaceutical plant, which might demand a MAR of 25%, whereas a stable public utility of, let's say, water treatment might require only 8%. Our rule is simple: if the project's IRR is greater than the MAR, we accept it. Coming to the fifth slide of CAPEX, OPEX, and total cost estimation in chemical plants. In process engineering, we divide cost in two categories. One is the capital, that is one-time cost, and second is the OPEX, that is operating expenditure. And for example, the actual equipment like reactors only account for about 30 to 40% of the CAPEX. The rest is installation, piping, instrumentation, and OPEX is the annual recurring cost, which is like where raw materials are the biggest factor, often hitting near 60% of the total. And by combining this, we find the total annual cost, that is OPEX plus CAPEX, which is our primary objective function, where we optimize process designs to find the most effective and operating condition.
Malin Christian, and now I'll be talking about the following slides. Uh, Present worth, first I'll be talking about present worth analysis. Present worth is commonly used method in chemical engineering economics. The idea is simple. We convert every future cash flow back to its value today using our minimum attractive rate of the return as a discount rate. The following the formula shown in this slide sums all the future cash flows divided by 1 plus I to the power of 2. If the result is positive, the project creates value. We accept it. Negative means we reject it. In our example, a distillation column costs 5 crore upfront, saves 1.2 crores annually for 8 years, and has a 0.5 crore salvage value. Plugging in at 12% mark gives us a present worth of 1.16 crore. So positive. So we accept the investment. Moving on to future worth analysis, future worth does the opposite. Instead of bringing everything to today, we push all the cash flows forward to the end of the project life. It is particularly useful when a company wants to know what the project will be worth at the end of closure, or to plan reinvestment. Future worth is simply present worth multiplied by the FYP factor. Crucially, future worth always gives the same except such reject decisions as present worth. They're mathematically equivalent. Our two examples confirm this. The petroleum refinery gives positive 11.87 million, and the fertilizer plant upgrade gives a 3.38 crore profit. So both are positive, so both can be accepted. Moving on to annual worth analysis. Annual worth analysis converts everything into a uniform annual amount. Think of it as spreading the entire project cost and benefit evenly across each year of its life. The formula has two key components: capital recovery, which analyzes the initial investment, accounting for salvage value, and the annual operating cost, which covers maintenance, utilities, labor, and raw materials. Annual worth is especially powerful when comparing equipment with different lifespans. Here we compare two heat exchangers. Shell and tube heat exchanger runs for 10 years, plate and frame only for 6. Despite Shell and tube heat exchanger costing more upfront, its annual worth is minus 6.4 lakhs versus minus 8.01 lakhs for plate and frame heat exchanger. Lower annual cost, so Shell and tube heat exchanger wins. This comparison is completely valid even though the lifespans differ. Real plant costs don't stay constant, they escalate. So gradient series handle this. An arithmetic gradient adds a fixed rupee amount G each year, like an aging compressor needing increasingly expensive maintenance. A geometric gradient applies a fixed percentage increase, common for fuel and energy costs with annual inflation. IRR is the interest rate that makes present worth exactly zero. It is the annual return the project earns. The rule is simple. If IRR exceeds MAR, we accept. In our solver recovery unit, IRR works out to be 16.3, which beats our 12% MAR. So we accept. The payback period of 4.2 years also clears our 5-year target. Both indicators confirm viability.
Hey everyone, I am Aman Jaiswal from Group 2. So we were discussing about the optimization of the plant designing. So our first topic is the reactor economics and process selection. Uh, Choosing a reactor is one of the most capital intensive part of the plant, and we use annual worth to compare them. There are three types of the reactor. The first one is batch reactor. Batch reactor has low capital expenditure. It's around 20 to 40 LPA, and operating expenditure is typically high because of its downtime, and it is suitable for the pharmaceutical industries, specialty chemicals, and small volume industries. And the second one is CSTR that has the moderate cost, ideal for the liquid fluid and reaction at steady state. So yeah, it's like a intermediate between the batch reactor and PFR. And the third one is PFR. It has higher capital expenditure but the lowest OPEX, I mean operating cost for the high throughput process like gas phase reaction. The decision logic, like the example that is given for this page slides, like in the provided example for an acetic acid, the PFR is selected because it offers the lowest average worth cost. It's around 18.2 liter per year compared to the CSTR. Yeah. So coming to the next slides, which is energy integration and heat exchanger networks. For like energy accounts for 15 to 25% of the plant's operating cost. These slides explain how we justify spending money to save energy. We can do pinch analysis. We used to find the minimum hot and cold utility targets uh, before designing the networks. And there is trade-off between the capex and opex, which is capital expenditure. Like what is, I mean, buying more heat exchanger, and opex is like something like paying for the steam cooling. And we have given a one table that demonstrate analysis of the overall the cost. It's like a there is given the comparison between the before integration and after integration cost. The before integration, the total annual energy was 67 liter per year, but after pitch integration, we have got 20% less than of the uh, previous energy cost. So yeah, that I was discussing that how the energy integration that can help and give a major contribution in our product profit calculation. And yeah, so by spending 30 liter on three new exchanger, a refinery saves 28 liter per year. This leads to a payback period only 1.07 years and massive present worth of 58.2 lakhs. And coming back to the next slide, which is demonstrate how the environmental compliance and carbon costing helps to explain overall the cost of the industry. Like modern engineering economics must include the cost of being green. If you don't account the carbon taxes and or waste treatment, you are understating the true project cost. In India, the carbon prices is somewhat around 400 to 1200 per ton of CO2. For a large plant, for the present worth of these taxes over 20 years can even actually exceed cost of building the plant itself. And if uh, if you are talking about the law, effluent treatments like and zero liquid discharge, compliance is mandatory. While generally, which is a zero liquid discharge system, are expensive. They are often cheaper than fines. The key rule is always include the NPV, which is net present value of avoided penalties and carbon taxes in your calculation.
Hello everyone, I'm Ati Joshi and I'm going to explain about chemical plant life cycle cost analysis. So in this slide, I'm going to explain about one of the most important ideas in chemical engineering economics, which is that a plant should not be evaluated based only on its initial cost, but on its entire life cycle cost. So a chemical plant typically operates for 20 to 30 years, and during this time, costs occur at different stages. And so we divide the life cycle into phases. First is the pre-feed or pre-feed stage, which includes feasibility studies and detailed engineering. Even though no revenue is generated here, costs can be typically high to from it can be around 10 to 50 crores. These are early stage investments, so we evaluate them using present worth. Next comes procurement or construction, where the plant is actually built. This is the largest cost component, often between 100 to 500 crores, and represents the major capital expenditure. After that, we have the commissioning and startup. During this phase, the plant is tested and gradually brought to a full operation. However, production is not optimal yet, so there are losses in terms of efficiency and missed revenue opportunities. Then comes the normal operation phase, which is the longest phase lasting up to 20 years. Here, the plant generates revenue, but also incurs recurring costs like raw materials, labor, utilities, and maintenance. Since there are annual costs, we analyze them using annual worth. In the middle of the life cycle, we may also have revamps or expansions, where additional investments are made to improve efficiency or increase capacity. These are evaluated using economic analysis. Finally, at the end of the plant life, we have decommissioning, which includes shutdown and environmental cleanup costs. These are future liabilities, so we evaluate them using future worth. So by converting all these costs into a common economic basis, we calculate the total life cycle cost, which gives us a much more realistic picture of the profits for profitability. So in this slide, I'm going to focus on handling uncertainty in chemical engineering projects using sensitivity and break-even analysis. In real-world projects, parameters like capital cost, revenue, operating cost, and interest rates are not fixed. They can vary due to market conditions or technical factors. Sensitivity analysis helps us understand how changes in these parameters affect the overall project outcome, such as present worth or annual worth. For example, if we vary the capital cost by plus or minus 20%, we can see how much the project profitability changes. Similarly, revenue is usually the most sensitive parameter. Even a small decrease in revenue can significantly impact the project viability. From this analysis, we identify which variable are most critical. Typically, revenue and interest rate have high sensitivity, while salvage value has relatively low impact. This im- this helps this basically helps engineers to focus on controlling the most important factors. The second part is the break-even analysis, which is used to determine the minimum conditions required for a project to be viable. In this example, we are solving for the minimum annual revenue, such as that the present worth becomes zero. When the present worth becomes zero, the project is neither making profit nor loss. This is called the break-even point, where the project is neither profitable nor is it generating loss. From the calculations, we find that the minimum revenue required is around 61.9 lakhs per year. So if the actual revenue is higher than this value, the project is profitable. Otherwise, it's not. Together, the sensitivity and the break-even analysis provide a deeper understanding of risk and help in making more robust and informed decisions. So in the next slide, I'm going to talk about the four major economic analysis methods used in chemical engineering, which are present worth, future worth, annual worth, and internal rate of return. And these help us understand when and why. And I'm going to explain when and why each method is used. First, looking at the reference point, it evaluates cash flow at different time bases. Present worth converts everything to today's value, which is time zero. Future worth converts everything to the end of the project life, and annual worth expresses everything as an equivalent uniform yearly. While while your internal rate of return is different because it does not convert to a specific time. Instead, it gives a rate of return. Next, in terms of units, present worth and future worth are expressed in monetary terms like rupees, dollars, etc. Whereas annual worth is expressed as rupees per year, which makes it very initiative for comparing yearly cost. Whereas our return rate, on the other hand, is expressed as a percentage which represents the profitability of the investment. All three methods, present worth, future worth, and annual worth, require an MARR, which is the minimum acceptable return of rate of return. This is because they depend on interest rate to convert cash flows. My internal rate of return does not require MARR during calculation, but we still compare internal rate of return to the minimum acceptable rate of return afterward to make a decision. Now, coming to the best use of cases, present worth is most commonly used for overall project feasibility and go or no go of decision created today. Future worth is useful when we're interested in the accumulated value at the end of the project, such as in long term planning. Whereas my annual worth is particularly useful when comparing alternatives of different lifespans because it converts everything to a uniform yearly basis. And my internal rate of return is mainly used for ranking and comparing multiple investment options. Now, another important factor is how these methods handle different project lifetimes. Present worth and future worth require adjustments like least common multiple or steady period methods. Whereas annual worth can directly compare alternatives with different lives, which makes it very practical in equipment selection. Internal rate of return, however, does not handle differing lifetimes well without additional adjustments. In terms of ease of calculations, present worth and future worth and annual worth are relatively straightforward once the formulas are well known. However, internal rate of return is slightly more complex because it requires iteration and trial and error to solve. Finally, the decision rule is very simple and consistent. For present worth, future worth, and annual worth, if the value is greater than zero, we accept the project. For internal rate of return, if the rate of return is greater than the MARR, the project is acceptable. The most important takeaway from this comparison is that all these methods are mathematically equivalent and will always lead to similar decisions. The difference lies only in how the results are represented, how the results are represented. So as engineers, we choose the method based on the context of the problem, not because one method is better than the other, but just because how we want to solve the problem. So now going to the next slide. In this slide, I'm going to talk about how economic equivalence methods are actually applied across different sectors of chemical industries. So first, I'm going to talk about oil and gas refineries. Present worth analysis is commonly used for evaluating refinery upgrades, such as installing new catalytic cracking units. Future worth is used for long-term projects like pipeline, while annual worth helps in selecting equipment like compressors. Now, going to the petrochemicals, these methods are used to compare different reactor types, such as batch versus continuous reactors, and to evaluate large investments like ethylene crackers. Now, in pharmaceuticals and specialty chemical sectors, annual worth is commonly used for evaluating systems like solvent recovery units, while present worth is used for high-cost investments such as clean room systems. Now, in fertilizer plants, future worth analysis is used for long-term upgrades like ammonia synthesis loops, and annual worth is used to compare energy efficiency improvements. In the polymer industries, engineers use present worth to analyze trade-off between downtime and capital investment, especially during product changeovers. And now finally, going to the effluent treatment or the environmental applications such as zero liquid discharge or effluent treatment, annual worth and present worth are used to justify the high cost of compliance and sustainability. So overall, these economic tools are not just theoretical concepts; they're widely used in real industrial decision making across all areas of chemical engineering.
So I'm going to handle this conclusion part for this presentation. So in the last three slides, we have this case study refinery capital investment decisions. So basically a petroleum refinery must cost between upgrade hydrotreater and install energy recovery system. As you can see here, we have a different table for each of this option A and option B, that is energy recovery and hydrotreater. So initial costs are given, that is 85 lakhs and 60 lakhs. So both these costs depends on what you want to do. Either you want to do the hydrotreater and the energy recovery. After that, we have the present worth that includes different kinds of costs, and in total we have 14.37 lakhs and 8.55 lakhs. So all these things depends on the future worth. So you have curves, the green one that represents the present worth and this orange one that represents the average value that is in lakhs per year. So in the second slide, we have engineering economics equivalence factor. So this includes various parameters like single payment, uniform series, capital recovery, sinking fund, and automatic gradient. So each has a different symbol and a different kind of formula that we're going to use for the further calculation. We have used in like chemical for salvage, lump sum, future expansion cost, annual cost savings, sinking fund, equipment loan. And we have these different converts that we need to perform like F to P, A to P, and A to F depending upon what kind of factor we are dealing with. And the last slide that we deal with in this presentation are economic equivalence, that the time value is the bedrock of all the engineering decisions, all the things that we're going to see here. Then we have this PW, FW, and AW, like all three methods are mathematically equivalent and always lead to the same decision. Then last, we have this environmental costing that involves carbon taxes, ZLD costs, compliance penalties, are real OPEX times, and etc. And in the final, we're going to talk about this green projects. So green projects and all depends upon all the future sustainability that we're going to talk about in the upcoming projects, which includes green H2 renewables evaluated with the same PW, AW, IR, and everything else apart from this. So that's all from the PPT that we made here.